Come on. Hey, all right, that's it. We're in. How's it going, guys?
Yo.
Thank God for Justin for doing his GANs presentation today. So yeah, this is President Ho.
Thanks. Good one. Good one.
Nice. So yeah, Justin, take it away, man. If you want, you can stand. You have room to stand. And
I'll sit. I think
All
I'll
right.
sit. But yeah, I'm Justin. I'm the big guy in charge. If you've only gone to ML Mondays, I'm the guy who would pay Kyle's salary if we got paid. We don't. But yeah, there's going to be a presentation about the legendary GANs, which I'm sure you've heard a lot about since they're quite common.
Can you go sit over there? You're in the camera shot. Sorry. That's my.
So rude, Kyle.
I'm also gonna move. This is just Justin's presentation.
Okay.
Sorry about people.
Brutal. I'm alone now, as it usually is.
Sorry about that.
So
Just so scuffed.
It's very scuffed. It's okay.
Okay.
But yeah, let's talk about GANs.
Son of a bitch. All right, there we go.
Whew. So, as you know, I'm sure everyone knows, with the advent of ChatGPT, DALL-E 2, Stable Diffusion, literally everything, kind of generative AI has never been bigger than now. This has probably been its spotlight and the biggest it's ever been. And so, as you can see, yeah, as I mentioned, tools such as kind of Stable Diffusion and DALL-E let us draw images using nothing but text. Tools such as ChatGPT offered like the first like real advanced chatbot that actually, you know, is knowledgeable and you can question and ask it stuff and it'll give you kind of valid feedback. And it's important to kind of like understand kind of where we're coming from, that and all the kind of research that kind of built up to generative AI and built up to Stable Diffusion. And so one of the earliest kind of examples of generative AI within the past kind of 2 decades is with GANs, which was pioneered by Ian Goodfellow and his colleagues at Google Research. And it eventually led to a lot of kind of the first kind of big iteration, first big breakthrough for kind of visual generative AI, which is this website called This Person Is Not Real, and then which is where this image is generated from. He's very real. You should trust me. He's not fake, and he's not sampled from a bunch of data. So again, I kind of touched on it before, but it's important to kind of emphasize. So GANs are still like quite common, even though they've been a little bit outclassed by the diffusion model, which kind of came into prevalence in recent times from a famous OpenAI paper that's literally called Diffusion Models literally outclass GANs on image generation and synthesis. But regardless of that, they're still quite state-of-the-art in some key machine learning tasks. And if you go on the website Papers with Code, you'll still find that for a lot of language tasks, they're still quite common as well. And so, yep, they've been used for stuff such as text generation and forecasting, and stuff of the kind of nature when it involves kind of you need to generate, as the name implies. And then, yeah, adversarial techniques are actually quite common in as like a field of literature and exploration. So a lot of research has been inspired by the way GANs are formulated and the adversarial technique that they use, since we'll cover it more in depth, but the way it actually works is fundamentally very different from typical machine learning. And then, yeah, GANs also are kind of the perfect intro, in my eyes, of density estimation, which is the big machine learning task and is basically kind of what, in my opinion, half of machine learning is. It's just guessing some density that we don't know. And again, while it is old, she still is quite significant and important to learn. Oh my gosh. Yeah. Double clicking. Okay. But let's back up. Let's talk some context before we get into kind of GANs. So it's important to kind of understand the subtask, which I'll describe to you, which basically will become the task that GANs seek to solve. But let's talk random numbers. So computers actually, like, in case you weren't aware, their background, the first kind of analytical computer was invented in the, I think, 1800s by Charles Babbage, the analytical engine and the difference engine. I don't think, one of them wasn't completed. But essentially, computers, due to that kind of inspiration, like that heavy mathematical background, are designed to be very deterministic, right? And you kind of expect that from your functions. If I have a function that determines if a number is odd or even, I expect that putting in 6 every single time will yield an even like answer from that function. And so kind of with that property in mind, however, the deterministic property in mind, it's pretty hard to make a computer be random because random is not deterministic. It's truly, like, it's the antithesis of that. And so it's actually impossible for most computers to be truly random. And of course, like, if you've been coding or you've dealt with kind of random number generators, like, it would be pretty problematic if we weren't able to do this. And so a lot of people, way smarter than I, have developed a class of algorithms that generate what we call pseudo-random numbers. Now, pseudo-random numbers basically simulate real randomness, but again, they're not random because typically these are seeded and they're using algorithms such as the Mersenne twister algorithm, which takes in like a random seed, and then based on this random seed or this random event, it generates a random sequence of numbers. But if you basically kind of lock the seed in place, the numbers won't be random, and you'll be able to kind of store and run it infinitely, and you'll be able to basically anticipate the numbers. Oh my gosh.
I think you have to aim it towards here.
I'm just gonna manually click.
Yeah, that's fine.
So, kind of the random number generators of computers actually can only generate numbers from a uniform distribution. And that's cool and all, but that's not really useful for what we want to do. Like, if you want to examine stuff that is not a uniform distribution, then you're kind of out of luck. But again, people who are way smarter than me have thought about this. And so there's a lot of techniques to kind of transform uniform random variables, or just random numbers, or yeah, variables from the kind of the uniform distribution into into distributions that are more interesting and kind of more complex. And so the kind of biggest technique that almost all modern computers use is the Box-Miller technique, which is used to kind of basically transform the uniform numbers that computers can generate into a different distribution of our choice and to sample from that distribution. And you have rejection acceptance and inverse transform sampling, which I'll be covering in kind of like detail. But essentially, inverse transform sampling, like Box-Miller and rejection acceptance, is a technique to transform a uniform random variable into a different random variable from a different distribution. So I put the definition online for inverse transform sampling, but essentially it's a technique that allows us to write or to generate samples of random numbers from any probability distribution as a function of the uniform probability distribution, as long as we know it has a CDF. So in other words, what we're trying to say is we can use inverse transform sampling to basically represent any distribution we want, as long as it's defined and it has a CDF function associated with it. And this is important because this essentially lets us solve for, and basically analytically solve for, a lot of the distributions that are important to us. Things such as normal, exponential, and Gaussian. We can all kind of write that in terms of the inverse transform sample, and we can sample from that, allowing us to represent these distributions that computers cannot natively generate from. Oh no.
Justin switching rooms on the team? Hello?
Howdy.
So, how's it going? The camera's right here, so.
Share.
Here, yeah. This is.
Thank you.
Yeah.
Here.
Alright, how
Alright.
much did I miss?
I'm still in like the context part, but I can
Yeah.
re-explain it.
That'd be great.
Yeah.
I love that.
You just move over there real quick. Yeah, the camera's like right there. Okay.
Let me go back a little bit.
Should be good now.
Aha.
Yeah.
Okay, we're good?
Yeah, we're good. Yeah, it's just on the camera. So it's fine.
Gotcha. So, yeah. So what you missed essentially is I was kind of covering like a sub-problem that we'll use to extrapolate and explain the problems that GAN seeks to solve. But essentially, we were talking about the problem of random number generation and how computers actually cannot randomly generate numbers. All of it's fake randomness, something that we refer to as pseudo-random, and it's all algorithmically generated. We seed these algorithms with a random event to kind of simulate randomness, usually with your computer's time, but these aren't truly random. And we also mentioned that computers can only actually natively generate numbers from a uniform distribution. Like, that's what they're quite good at and what these algorithms do, but they cannot natively generate from distributions that are more complex than uniform, like Gaussian and exponential.
That's interesting. I
Right.
can do that.
Right. So obviously that's a pretty big deal because if you're like any like sane person, you probably need a distribution that's more complicated than uniform to do any like work that is meaningful. So people have developed a bunch of techniques to convert a uniform random variable or a uniform distribution into a distribution that is more complex. And so these techniques are called Box-Miller, rejection and acceptance, and inverse transform sampling. And these techniques essentially allow us to represent like a normal distribution in terms of a uniform distribution. So it's some function that takes in a uniform random variable and it spits out like it basically spits out like as if you were sampling from like a normal distribution or an exponential distribution. That's how computers actually like sample from non-uniform distributions. They use Box-Miller, which is like the fastest algorithm, but the simplest one in my eyes, other than rejection acceptance, is inverse transform sampling, and that involves it's just the definition. But essentially, inverse transform sampling allows us to write like complex distributions, like exponential functions or exponential distributions, Gaussian and normal distributions, in terms of a uniform distribution, like analytically. You basically solve it out as long as it has a cumulative distribution function. And so what this is essentially saying is if the distribution is defined and it has a CDF, we can basically solve for an inverse that will allow us to transform from a uniform distribution to that distribution. And that's how you sample from more complex distributions. So I originally adapted these slides for Swamp Hacks, and this was my big catfish. I'm going to spend the first half just covering all this math stuff, unrelated to GANs. But the big connection is inverse square transform is essentially a technique to kind of go from one distribution to a distribution that we want. And again, the big weakness of this technique is that the distribution needs to be defined, right? You need to know it beforehand to analytically solve for it using either inverse transform or Box-Miller. Now, if you don't know, then you're kind of out of luck. These tools in our toolbox don't really work. And so GANs were invented to essentially do the same thing. They were invented to take in kind of a noise vector, use machine learning, and to find this distribution that is far more complex, far larger, and to basically kind of approximate it and then spit out like a sample from that distribution. And yeah, they're basically GANs and inverse transform sampling, which I do have more math heavy examples in the notebook after, but they both solve the same problem. They both are the problem of transforming one simple distribution that I can do, and I do know very well, the uniform, into something way more complicated. So, what do my friends have in common?
They're the same person.
I don't know, maybe if you squint your eyes really hard. What do they have in common? This isn't a trick question.
They're all made of pixels.
They're all white.
Okay, think a little more simple here. Well, they are all white, that's true. What else?
They're all looking at the camera direct head on.
Yeah, pretty much. What else? Like, think simply.
They're all pictures.
Okay, not that simple. Like a little more, like think about like what makes them like same. What do they have?
People. Same dimensions.
What about people?
They have eyes and nose and mouth.
Yeah, that's exactly. They all have eyes, nose, and mouth. So kind of the purpose of this assignment is to establish the concept of similarity. So so let's say we're kind of examining the task of generating images of people that have never existed before. In order to even think about doing it, you have to establish the notion of similarity of this task. And so what we just did was establish that these people are similar. Why? They all have eyes, they all have nose, they're all white, they're all looking at the camera, they all have hair. And kind of with this in mind, if you kind of break it down, we can represent this probabilistically. There's an average person within these three images. If you merge all of them, there's an average person that exists. And there's probably a distribution that these people lie on. It can be very wide because we only have 3 people. But there is a distribution and there does exist like an average person. And if you examine this room, there's an average face. There's an average set of eyes, just by amalgamating and combining like all of our features together. And so once we've established kind of like this idea of similarity, we know we're grounded in probability and we have some mathematical basis we can work off of. And because we have this kind of idea that we're grounded in probability, we can approximate it. And so the distribution, unfortunately, for the average face, the average person, is probably like insanely complicated, right? If you consider things such as race, different hair colors, piercings, like glasses, no glasses,
No hair.
no hair, skin color, like eyebrows, no eyebrows, like that's so like there's so many features you have to consider, and even things that are subtle like face shape that we probably can't comprehend what that distribution would look like. So the actual distribution is like something insane, like one of these objects where we cannot physically like, envision it because it's so complex. But what do we have in our toolbox that can and that works for kind of approximating kind of distributions or just functions that are like impossible for us to understand? We have machine learning, we have deep neural techniques, which their whole bread and butter is to be able to kind of, you throw these massive data sets and they're supposed to be able to extract these crazy relationships between these massive sets of data. And so kind of the idea of machine learning lends itself pretty naturally to this task. And so here comes the GAN architecture. So kind of to back it up a little bit, so before we kind of cover GANs, you might think that the kind of classical machine learning technique is like I have my answers, and then I have my test, or not my train, my y and my x, and I pass it through like one function, and then based on what the model says, I compare it with the y and I back propagate. That's a typical paradigm for kind of machine learning for like things such as image classification and for a lot of tasks. However, that kind of architecture kind of falls apart when you're dealing with GANs, because if you think about it, you're kind of faced with two big problems. So with GANs, I have a subset of images, and let's say I pass in like a noise vector into my machine learning model and it spits out an image. Well, how do you compare two images as being different in order to back propagate in like an error? Do you just average the mini batch of like images and try to propagate that backwards? Do you kind of get like an average distribution that those images lie on and back propagate it and then see how that works? Well, that's actually been tried with I think they're called the Gaussian mixture networks, which were the predecessors to GAN, and that's the direct approach, like the most like intuitive approach that most machine learning engineers think of when they solve a problem. But the big issue with that approach is you run into the issue of the curse of dimensionality, because if you think about it, like that subset of images that you collected to train your model on is tiny. It's minuscule compared to the true distribution of what those images actually lie on. And so you lose a lot of information that way, and you're going to need a lot more images to actually like accurately like do this back and forth. And also, in order to do the calculations and compare like the average distribution of images versus the distribution of this image I just generated is super computationally expensive, and it just doesn't work in experimentation. Maybe there's something there to be explored in the future, but people have looked at it briefly and were like, this is not like great. And so Ian Goodfellow, and I think it was 2012 or 2011, he developed the GAN architecture, which is actually quite elegant and seeks to kind of get around that whole issue that I mentioned with the curse of dimensionality, and to get around the issue of the cost by kind of creating this kind of simple game that you have two networks play against each other that implicitly solve the problem for solving for this distribution. And so the GAN, again, it consists of two components, two big models. You have a generator, which takes in a random seed or a random noise vector, and then it spits out a fake image. And now after you have your fake images, those fake images are passed with our real set of images into a discriminator. And as the name implies, the discriminator's job is to discriminate. It's to basically just say, hey, is the image I'm seeing right now, was it built by the generator, or was it from our true distribution? And based on kind of that output, the binary real or fake, that error is propagated back out through the discriminator first, and it trains itself to be better at recognizing real and fake images, and then it uses that feedback to also kind of train and update the weights for the generator. So essentially, the discriminator is serving as a guide to the generator and telling it what it needs to do better. For example, if I want to generate pictures of people, and I have a real set of pictures of people, and I have a generator that's horrible at what it's doing. It generates dogs for some reason. That's crazy. I don't know how it did that. But you pass it into the discriminator, and the discriminator is going to say, okay, like that dog, why does that human being have fur? Like that's weird. And it's going to basically implicitly back propagate that error. It's going to say, hey, Like, I know that is not a person because he has fur and he's on 4 legs. And that error is essentially going to be implicitly backpropagated into the generator, and the generator is going to learn, hey, human beings do not have hair. That's what got me. So to be better, I won't do that. And yeah, this is pretty much what I just covered. But again, the discriminator kind of doesn't, the discriminator's purpose is to serve as a guide. It's basically say, hey, are the images like good or are the images bad right now? But the discriminator doesn't actually know the distribution of the images. That's for what the generator's purpose is. And you pass in a random noise, and it's more commonly referred to in the literature as a latent space, which is essentially just a random noise vector of like a certain dimensionality. Typically, I think it's 100 by 100, and it's passed into the generator, and the generator does some transform function that it approximates and creates an image and sample. It stores a distribution of images and it samples from that. And again, this is pretty much what I mentioned, but the discriminator processes real or fake images, and it gives guidance to the generator on what it should do better and what it should do worse. So I have like the rough training steps. So I was trying to keep it simple and classy for the swap packs people. But this is kind of the typical steps that you would take if you're trying to set up a GAN. You set up your 2 models, generator and discriminator. So in terms of both, the kind of meta or the big architectures for at least visual kind of GANs is to use convolutions and deconvolutions or convolutions in the case of the discriminator, which is pretty typical, and deconvolutions for the generator to kind of upsample like your noise vector. And again, so the training step would go, you generate some uniform or normal variable in your training step, and you pass that into the generator, and it's gonna spit out just like noise because it's not gonna be trained at this point. And you have your mini batch of kind of noise images, and you pass that along with your real like mini batch of images into the discriminator. And because you already know the labels of both, since they're kind of, the fake images are generated separately from the real images and they're not mixed in, you can pass it in with a label to the discriminator, and the discriminator first back propagates at the errors of real or fake against itself, and it improves that way. And then you freeze the weights of the discriminator and you do it again, except you freeze, the discriminator's frozen, and you back propagate that error into the generator. And you just keep repeating this until you reach a quality that is good of images that you like. And so the tricky part about GANs is their error really doesn't mean much, because you have 2 errors. You have the error of the generator and the error of the discriminator, but typically, due to the process in which they learn, it's like the numbers typically are much trickier to discern meaning from, versus like a typical classifier where if you just drive that number like real down small, you know it correlates pretty much with like performance. Hello.
Yeah, something showed up on the screen.
And so GANs, while they are like brutally simple, they do suffer from a couple of major problems. And so one of them happens when the generator gets too good and the discriminator kind of just like is completely outclassed. But in that case, the generator just fools the discriminator every time. And so at that point, you just have to implement early stopping, or else what will happen is the discriminator doesn't know what it's doing. It's just gonna back propagate some error that is probably incorrect, and the generator will get affected by that. And so that's something that's like standard practice. You should have a early stop implemented for your GANs, and typically that's done using timing, or you can also have like manual early stopping, is what I've seen people do. And then there's another big issue where the discriminator gets too good. So if the discriminator gets too good, and then you just suffer from vanishing gradient pretty much. Like the error that's back propagated from the discriminator is pretty small, and it's not really shifting the weights of the generator, so you don't really progress in training. And then the next big one that's pretty exclusive to GANs is called mode collapse. So essentially, in kind of the game that the discriminator and generator play, sometimes the generator will kind of find like an ace in a hole. It'll basically discern that, like, let's say I'm generating pictures of dogs. My discriminator just sucks at like discerning images of poodles as fake. So I'm just gonna learn to infinitely generate poodles because that's how I score perfectly. And so mode collapse is essentially the issue of like a generator that has low diversity in what it generates, and it just only spams one class because that maximizes its objective of fooling the discriminator, even though that's not what we want. But that's what the generator was trained to do. That's what the formulation says it has to do. And so this is a more pressing issue, and it involves architectural changes. One of the biggest changes that people kind of came up with was the unrolled GAN architecture, which is pretty complicated. But the other simpler one, which was done by Goodfellow again, and I think it was a 2014 or 2015 paper, was the Wasserstein GAN, where he actually changed the loss function out, since in the original formulation he used cross entropy, which had bad properties that kind of contributed to mode collapse. The Wasserstein loss kind of alleviated a lot of that and prevented a lot of mode collapse, the issues that you see with that. And so I'm gonna steal your laptop.
Is that okay?
We're almost there.
Yeah.
So overall, kind of GANs are very interesting. It's a very, very strange solution to quite a complex problem, and it's quite elegant in my eyes, because instead of again approaching the problem of density estimation from this direct machine learning technique, where you again you know your answers and you just backpropagate your answer against your answers into the model. You have two competing models and they implicitly solve for a distribution that you don't know. That's quite elegant to me. And yeah, this is again the textbook example of a density estimation problem. Yeah, this is again the textbook example of a density estimation problem.
Sorry.
Yeah, this is again the textbook example of a density estimation problem. Yeah, this is again the textbook example of a density estimation problem. Yeah, this is again the textbook example of a density estimation problem. Yeah, this is again the textbook example of a density estimation problem. Yeah, this is again the textbook example of a density estimation problem. Yeah, this is again the textbook example of a density estimation problem. Yeah, this is again the textbook example of a
It's showing a school.
problem. Yeah, this is again the textbook example of a
It's showing a school.
problem. Yeah, this is again the textbook example of a
It's showing a school.
problem. Yeah, this is again the textbook example of a
It's showing a school.
problem. Yeah, this is again the textbook example of a
It's showing a school.
problem. Yeah, this is again the textbook example of a
It's showing a school.
problem. Yeah, this is again the textbook example of a
It's showing a school.
problem. Yeah, this is again the textbook example of a
It's showing a school.
problem. Yeah, this is again the textbook example of a
It's showing a school.
problem. Yeah, this is again the textbook example of a
It's showing a school.
yeah, this is again the textbook example of a
It's showing a school.
yeah, this is again the textbook example of a
It's showing a school.
yeah, this is again the textbook example of a
It's showing a school.
yeah, this is again the textbook example of a
It's showing a school.
yeah, this is again the textbook example of a
It's showing a school.
yeah, this is again the textbook example of a
It's showing a school.
yeah, this is again the textbook example of a
It's showing a school.
this is again the textbook example of a
It's showing a school.
this is again the textbook example of a
It's showing a school.
this is again the textbook example of a
It's showing a school.
this is again the textbook example of a
It's showing a school.
this is again the textbook example
Why
this is our typical GAN architecture. And so the generator only takes in our noise vector. But with the conditional GAN, it takes in an additional label. And so, let's say I want to, or I have like images of like cars that I just know because
Sorry, I'm not just.
images of cars that I just know of because they're pre-labeled, because they're from the Cypher 10 dataset.
Mm-hmm.
So I can basically get my like 16 car images, right? Because I know their labels, and I can kind of set them here. I have 16 car images. I can basically pass in this random noise vector, or my 16 random noise vectors, along with 16 car, this is 16 car labels. So this is gonna correspond to some number, like 0 to, or well, depending on if you're doing 1 hot, but like typically like 0 to 10, and let's say that it's just 1. So by doing the simple act of passing in like an extra like conditional variable, this 1, the generator reorganizes its space. So the space for the generator, let's say it's without the conditioning, the GAN just kind of, it organizes its space like this. Pretty much where all classes of like images are kind of overlaid. And that makes sense, right? Because when I sample from a traditional GAN, you get what you get. You don't get control over the images. So whatever my random noise variable transforms into, in terms of like these classes, is what I'm gonna end up getting. However, with conditioning, pretty much one, they've like projected the space that like GANs learn, and it separates out the classes a little more. And it also basically allows the generator to pick and pull. So for example, if this is my cars distribution, it knows that, hey, I need a sample from this distribution in order to generate images of cars. It's essentially a map. It tells it like a map on where to find the distributions that it
Is it a different distribution, or is it just like a different like peak or like part of one distribution?
So it depends on what tasks you're generating. For like humans, it's like typically 1, but for like multi-class, they're different.
They're
like
different distributions entirely. Okay.
Because if you think about it, like buses and like birds are very different.
Yeah.
So
okay.
it's hard to, yeah.
Right.
So that's one big class of GANs that are really.
Wait, don't worry.
Okay.
It's okay. It's okay.
What was your
I'll try to
question?
remember. So basically, the GAN takes in the noise vector, and that's what's it's transforming that noise vector
Correct.
into whatever X or image we're trying to create.
Yes.
But adding the car label allows it to kind of partition the
Perfect. Yep.
feature space. I don't think that's what I would think that is.
But yeah, it basically is like a map for the generator to be like, oh, this is where I put my distribution of cars. And then it
Okay.
allows it to pull from there at like the highest level view. It's a little more
Okay.
complicated than that, but.
So if it knows, it knows that the real data being passed in 16 cars, so it's just gonna give the fact that there's gonna be 16 cars to the generator.
Yep. And it's
Okay.
going to associate, hey,
Okay.
this is what cars.
It's gonna be like, I need you to create a car.
Yeah.
That's what you're gonna compare it against.
Yeah.
So if I make a dog, it's like, yeah, it's gonna be able to tell a dog from a car
Yeah,
pretty
it's-
easily.
yeah.
Okay, that makes sense. Cool.
And actually, the cool thing about the class of conditional GANs is before Stable Diffusion became big, the Stable Diffusion is like low key, kind of simple, but it was actually powered by GANs way before it was actually powered by diffusion models. So the way Stable Diffusion works now is you have what's called clip, which is a kind of big generative. It's kind of. I'd say it's more of like a discriminative or kind of generative network, but it basically takes in a set of text. And then clip was a model that was trained on like a bunch of images, so it associates text with images, right? So the original, or the current Stable Diffusion, the way it works is it's a clip model, and then it's a big diffusion model. It's a big diffusion model that's trained on like all these images, or it's conditionally trained on all these images, and this output from clip is passed into this diffusion model, and it generates like a cat riding a bicycle eating tacos. But before Stable Diffusion was a thing, this box was the GAN. So they're still quite,
So what did a clip do? Like given text?
Yeah, when you give it text,
Do you give it text or text embeddings?
you just text.
Just text.
I think it does like the embeddings for you. It
Okay.
like does all that. But it outputs I forget. I think it outputs just tensors that are associated with images. And so it
Okay.
originally was developed for like image generation.
Okay, so basically just from text it like kind of pulls up some images,
It
but then
feeds it.
but then the diffusion model takes the images and kind of like amalgamates them,
Or not the images. So I think Clip just generates numbers that only models can understand.
Okay.
So it says, hey, this is like what the input was, and this is my like language that describes what that was for like a GAN or a diffusion model.
Okay.
And the diffusion model takes that like value in, whether it be like in the form of like random noise or like a label, and then it like does processing on that and generates what you want.
Okay. That's
So that's just interesting because like the stable diffusion technology was always there.
mhm.
And it just got really good because diffusion models are leaps and bounds like better than GANs. But yeah, I think that's it. That's all I had.
Awesome. Thank you, Justin.
Yeah.
Let's go. Hey.